Now we have some tools in Seaborn to visualize univariate data. Let's further figure out how to visualize bivariate, or two-variable data, and multivariate data. This usually involves looking for relationships between two or more variables. We will focus on joint plots, pair plots, and heat maps. As a first technique, let's consider a joint plot. This joint plot features a scatter plot of the total bill and tip values within the axes. Above and to the right are histograms of the individual coordinates. Statistics like p-values and Pearson correlation coefficients are computed and displayed in the upper right corner automatically. Intuitively, the Pearson correlation coefficient quantifies how strongly two variables are correlated, and the p-value tells us the statistical significance of the difference of this value from 0. See our statistics curriculum for more details. The Seaborn command to create this plot is joint plot. The arguments to it are a data frame data and labels x and y for two of its columns. Joint plots can be tailored in the way they present the bivariate and univariate distributions for each dimension. Here, a technique called kernel density estimation, or KDE, is used to smooth the central scatter plot and the bounding univariate distributions. The KDEs that are computed result in smooth contour plots and surfaces instead. To produce the joint plot with KDEs, use kind equals KDE. Other options for kind include using a scatter plot, a regression plot, a residual plot, or a hexbin plot. With more than two variables, we may want to plot all possible joint plots for each pair of variables. The plot here displays pairwise scatter plots of the total bill, tip, and size columns from the data frame tips. These are the only numerical columns of tips. The others all have string entries, although they're all technically factors. Notice this 3x3 matrix of axes is symmetric. For instance, the size versus total bill plot is the transpose of the total bill versus size plot. The diagonal plots are histograms of the relevant columns. This can be created automatically with the command pairplot using the sole argument tips. Of course, many other optional parameters could be used as well. Notice that the pairplot command only used numerical columns to generate the pairwise plots. The remaining columns are intelligently ignored. This is part of the beauty of using pandas data frames with Seaborn over using NumPy arrays. Labels from the data frame are automatically propagated to plots or other data structures. A lot of the busy work with NumPy and Matplotlib has been taken care of for us. It's remarkably easy to stratify the data further in pair plots. In this instance, we can group the data by sex and redo the pair plots just by adding the keyword argument hue equals sex. The resulting plot displays the correlations between the tips, total bill, and party size grouped by sex. A final visualization technique we'll look at is a heat map. A heat map is more or less the same as a pseudo-color plot of a matrix with additional functionality for pandas data frames. This heat map depicts the covariance matrix for the numerical columns of our tips data, namely total bill, tip, and size. Notice the diagonals are all 1 in value, and the squares are colored symmetrically about the diagonal. Also, each square is labeled with the data frame's column headings. For the code, assume we have constructed a pandas data frame called covariance that stores this matrix with labeled rows and columns. You can review covariance matrices in our statistics curriculum. Roughly speaking, the entries of a covariance matrix quantify how strongly two variables change together. With the covariance matrix in memory, we need only to call heat map with covariance to get the preceding plot. Heat maps are commonly used to visualize covariance matrices for hundreds or thousands of variables, say for correlated stocks or gene expression. Now you've seen some visualization techniques for multivariate data in Seaborn. It's time to practice them in the exercises. We've seen a lot of visualization tools up to now. Now we're going to pull together these skills to work on visualizing some practical data sets. In particular, we'll work with some time series first and later with image data. Remember, pandas data frames have columns that are series that share a common index. Here, we're looking at a data frame of weather data in Austin, Texas, recorded hourly over the course of 2010. Notice when we look at the index of this data frame, it's of a specialized type called a datetime index. That is, the index is made of data structures that store times and dates explicitly. We'll learn some pandas ways of working with these shortly. We can plot all the columns of a data frame with the plot command. This plot is not that useful though because two of the curves are dense bands and the third is too small. Notice the dates are also labeled illegibly. When a series index consisting of date times representing dates and times, the series is a time series. Time series occur anywhere time-varying phenomena are measured, weather, stock prices, and so on. An important convenience of Pandas time series is that they can be sliced using strings to represent complete time periods. For instance, this first expression slices all 24 hourly measurements from July 4th, 2010. The second expression slices all hourly measurements from the 61 days making up March and April 2010 inclusive. And the third one slices the month of May 2010. Let's look at this way of slicing time series more closely. As an example, we slice the series temperature from the weather data frame. The slice in question, March_April, contains the temperature data extracted from the series for the months of March and April 2010. Remember, using the iloc bracket -4: to slice from the end of the series March_April, we see the last entries do correspond to April 30th. Now that we know how to slice time series, let's plot selected slices of the data. This is a plot of the temperature and the dew point over January 2010 with a legend. The dates on the horizontal axis are messy. We'll fix that shortly. Here's the code to make that plot. Notice we used a shorter slice of the longer temperature and dew point time series. We also used a legend to make the figure clearer. Now let's fix the messy axis tick marks from the last plot. In the first line, we slice from the month of January 2010 from the series temperature. Next, we use the slicing idiom, (::96, to extract a slice with stride 96 from the index of the time series. That is, every 96th element from that time series. Since the data is collected hourly, this picks out the start of every fourth day. Once the dates are extracted, we can convert them to a list of formatted labels using the stir_ftime method of the datetime index object. This method uses well-documented but cryptic format strings to convert datetime objects to human-readable dates or times. We print the labels out in the last line to make sure that we got the correct ones. We now redraw the plot issuing the same commands as before. Notice the dates on the axis label are concise strings and are rotated to be more readable. To make the preceding plot, we use the same plot calls, and before issuing show command, we call xticks with the dates and labels we just created. Notice we also use a rotation equals 60 argument to improve legibility. The value 60 is the angle in degrees by which the text labels are rotated from the default orientation, horizontal along the axis. For convenience, we will use the rotation argument to tidy date labels on all subsequent plots of time series. Now it's your turn to experiment with plotting time series.